Look at this heavy metal sphere resting on a steep concrete incline. A single string anchors it to the wall, holding everything perfectly still. But that stillness is an illusion. Even when nothing is moving, the setup is locked in a constant, invisible tug-of-war. There are three competing forces fighting for control at this very moment: gravity pulling the sphere straight down, the ramp surface pushing back up, and the string pulling it inward. To understand how this equilibrium actually works, we have to look past the physical objects and analyze the specific forces acting on them. If an engineer gets these measurements wrong, the string snaps or the ramp fails. They need to know the exact stress placed on these materials to ensure the whole structure won't collapse. We can map out our known variables on a 2D cross-section. We have the total downward weight of the object, W, the angle of the incline, alpha, and the angle of the string, beta. What we don't know are the two forces reacting to that weight: the exact tension pulling inside that string, and the normal reaction, R, which is the force of the ramp pushing back against the sphere. This presents a problem. We have two separate forces to calculate, but only one weight value to work with. We need a way to relate these three angles to the physical weight of the sphere. To solve for those unknowns, we strip away the physical reality. In physics, we reduce complex problems to pure geometry. This leaves a coplanar, concurrent force system. All three force vectors radiate from a single point on a flat plane. Because the object is at rest, these isolated vectors are in a state of perfect balance. To find the value of each force, we have to precisely map the 360 degrees of empty space between these arrows. First, we map the angles. Weight pulls 90 degrees from horizontal. Adding tension's angle beta creates 90 plus beta. The reaction force's angle alpha is subtracted from the 180-degree vertical, giving 180 minus alpha. Subtracting both from 360 leaves exactly 90 plus alpha minus beta. Every part of the physical setup, the sphere, the ramp, and the string, has now been translated into a coordinate on a geometric map. Now we apply Lami's theorem. This rule allows us to translate these geometric angles back into the physical forces we're looking for. The theorem states that in equilibrium, each force is proportional to the sine of its opposite angle. This gives a three-part equation: weight over the sine of its opposite angle equals tension over its opposite sine, which equals reaction over its opposite sine. These complex denominators can be simplified using trigonometric identities. Sine of 90 plus alpha minus beta becomes cosine of alpha minus beta. Sine of 180 minus alpha becomes sine of alpha, and sine of 90 plus beta becomes cosine of beta. This simplified equation connects our known weight directly to the two unknown values we must find. To find the tension pulling on the string, we isolate the first two parts of the equation. Rearranging them shows that tension equals weight times the sine of alpha divided by the cosine of alpha minus beta. We do the same for the normal reaction. By isolating the first and third parts, we find that the reaction force from the ramp equals weight times the cosine of beta divided by the cosine of alpha minus beta. These formulas now map perfectly onto our real-world objects. Physical stability isn't a passive state. It is a precise balance maintained by geometric laws. By using Lami's theorem to quantify these forces, engineers can move from guessing at a structure's stability to proving it through calculation. We've turned a visual observation into measurable, predictable data.